So yeah, so welcome to this live session. So continuing from the previous week, so roughly in the previous week, so that is week 10, what we saw was we introduced state space analysis. Okay, so writing the x dot is equal to ax plus bu form for any dynamical systems. So then we also have seen the linearization concept, linearization. Then we have seen the state transition matrix. Okay, so the pi of t. Okay, then we also have seen finding the transfer function. Okay, so these are the topics we saw in the previous week 10. Okay, so just continuing from the transfer function. Okay, so these are the two equations we have in the state space system, where the first equation is the state equation, second equation is the output equation. Okay, so if you take the Laplace transform considering initial conditions 0, okay, so we get the transfer function as this. Okay, d multiplied si minus a whole inverse b plus e. Okay, so where this requires the this si minus a is non-singular matrix. Okay, so if you write that si minus a whole inverse in its form, okay, so that is this form. So where adjoint of a divided by z. Okay, so you get this equation. Okay, so if you set this denominator equal to 0, the denominator means the data of si minus a equal to 0. Okay, so we get this characteristic equation. So we call the roots of this characteristic equation are poles of g of s, because it is a transfer function. Okay, so in matrix theory we already know that roots of this characteristic equation are nothing but the eigenvalues of a. Correct? So that means what? The poles are nothing but the eigenvalues of a. That is the conclusion. Okay, so directly given system matrix A, if you find the eigenvalues by using this Si minus A, okay, so determinant, so that is called as the characteristic equation. So the eigenvalues are also called as the poles of the uh, transfer function g of s. Okay, so directly we can decide the stability by using the eigenvalues of A matrix. Is this clear? Any doubt? Okay, so the poles of G of S are nothing but the eigenvalues of matrix A. If you just find the eigenvalues, so based upon the eigenvalues, we can directly characterize the stability of the system. Whether the eigenvalues are negative, positive, whether then we can say that they are on the left-hand side or right-hand side of the J omega axis. Okay, any queries?
No, sir.
Yeah, so this is what we saw till last week. So this week, so we are going to see these two important concepts, controllability and observability. And later, after seeing these definitions of controllability and observability, we are going to see two important design techniques based upon these controllability and observability. Okay, so basically, these controllability and observability, they are very important in a design of controllers in the control system. Okay, so basically they governs the existence of the solution to an optimal control problem. Okay, so in that you will understand in a while. So first let us see this controllability. Okay, so controllability basically it talks about existence of the solutions for the state feedback system. Okay, so particularly for placing the poles uh, to our desired locations. Okay, that is first aspect, controllability. Okay, then observability is, it will talk about observing or estimating the states from the output variable. Okay, or we can also call them as the measurable. Okay, so two aspects, controllability and observability. So once you see the definition, you will understand the two purposes. Okay, so first let us see these images. Okay, so consider the first top one talks about the importance of the controllability. What exactly the controllability? This one is observability. Okay, so you can see here in the top image. Okay, so where this image indicates, okay, image indicates. So we know this x dot is equal to ax plus bu. Okay, so to this x dot is equal to ax plus bu, that represents the plant. Okay, plant or system. To this we are applying this input u of t. Okay, then you get your output here. Let's say x. Okay, so from there, yes, you take the feedback. So this feedback, okay, so take this f as, let's say, some k. Okay, then giving it to this summing point. Okay, so you can see that image, and u of t can be written as r of t minus f multiplied x of t. That you can understand. Okay, from the summing point. Okay, so now you can see here. Let's say if you take, okay, so u is equal to minus kx. It means that what you're doing is, so if you take this u as minus kx, okay, and once you know u, you can substitute into this. Okay, so ax plus b multiplied minus kx. Okay, so then x dot is equal to a minus bk multiplied x. So let us call this is as acl, a closed loop. Okay, so my equation then turns out to be x dot is equal to ACL x. Okay, so this basically what we are trying to do here. So we are taking x here, that is state. Okay, multiplying that x with this gain k. Okay, and then here to the summing point, we are taking negative. Okay, this is what we are trying to do. Okay, so that we are saying it is as the uh, control input. Okay, control input. So that is basically based upon the state feedback. We are taking the state as the feedback and multiplying with u is equal to minus kx. Okay, suppose instead of minus kx, let us say if you take plus kx, what will happen? You will get plus here, correct? Okay, so when you get plus here, okay, so you will get the system response and increases unboundedly. Okay, so that's why instead of taking plus kx, we take negative kx, which is nothing but the negative feedback. Okay, here what basically the controller needs is, controller needs this x. Okay, controller needs this x, so that we call it as a state feedback. Okay, state feedback. So just wait for a moment here, then come back to the below image. Okay, here we are taking the, in the top one, we are taking state feedback. In the below image, if you see again, similar way. Okay, so we have this plan, we have this plant. Okay, so then from the plant, you will get, let's say, x vector. Okay, then you are multiplying that with some other matrix D. Then the output is y. The output is y. Okay, here if you say that u is equal to minus kx, you require directly the x vector. Okay, whereas here in the first image, you're directly getting x. Whereas here you're not getting X, instead you're getting Y output, some other variable. Okay. For example, here, let's say your Y is like this. Your Y is, so Y is equal to 1, 0, X1, X2. What does it mean? Your Y is nothing but X1. Okay. Here you're not taking the feedback of state. You are taking feedback of output. Whereas here you are taking feedback as state. Okay. So the question is, again, to do this analysis, okay, you require state X here. You require state X. So to find that state X, what we'll do is we will use this output. We'll use this output and estimate this state X cap. We'll estimate this state X cap using something called as the observer. Okay. Then once you have this X cap, we directly go like this. You will take, so U is equal to minus K X cap, then do this analysis. Okay. Closed loop control. Okay. So this, the top one is called as the controllability aspect. The below one is called as the observability aspect. Okay. So you'll understand more in the next part. Then again, you can come back to these two images. Okay. So just remember these two images and try to connect with the definitions of controllability and observability. Okay. Where in first thing we are using state feedback. Second thing is we are using the output feedback. Okay. And then along with the observer to find the state. Is this clear? Is this clear? Okay, once you understand controllability and observability, you will understand more of these two images. Okay, so let me explain that one first, then we'll come back here later. Okay, so first, state controllability or simply controllability. Okay, so this is the equation we have, state equation and output equation. Okay, in general, the standard definition for the controllability like this. Okay, you can read this. The state X, okay, the state X is said to be controllable at t is equal to t naught. Okay, if there exists a piecewise continuous input q of t, okay, that will drive the state to any state x of tf in the finite time tf minus t naught. Okay, so if every state x of t naught is controllable in the finite interval of time, then the system is said to be state controllable. Okay, it means in simple words, let's say your state is starting at x of state is starting at a time t naught. Okay, if there is an input, continuous input u of t exists, which takes the state from x of t naught to x of tf in the finite time interval. So tf minus t naught, then we can say that, okay, the state x is said to be controllable. If all the states are controllable, then we can say that system is state controllable. Okay, this is the meaning. Anyone having any query here? The definition. If you're having any query, you can ask me.
No, sir.
Yeah. So basically, let me repeat again. Okay. So state controllability means, let's say your system starts at initial time t naught with state x of t naught. Okay. If there is an input u of t exists, okay, u of t exists, which is piecewise continuous, which it takes the system from x of t naught to x of tf, then we can say that system x is system x is controllable. Okay, here we are talking about one state. If every state is controllable, okay, then we can say that the whole system is state controllable. Clear? Any query?
No, sir.
Yeah. So now what we do is for the given x dot is equal to ax plus bu. Okay. So this matrix is called as the controllability matrix. Yes. Okay. Controllability matrix. Okay. If we find the rank of that matrix, yes. Okay. So which goes like this: b a b a square b etc. a n minus 1 b. Okay. So if that rank is equal to n, then we can say that system is AB controllable. System is AB controllable. Okay. So this is the basic definition of controllability check. Okay. So the question is, how did you get this S matrix? Okay. So that you can watch the videos. Okay. So how the S matrix has been derived. Okay. Now what we see here is we saw the definition. Okay. So you can watch the video for from the definition how this S matrix came and how we are deciding that if the rank is equal to n, it is controllable. Please watch the video. Here we are going to see the example. Okay. Now consider this simple system. Okay. So we have x dot is equal to ax plus bu. Okay. So let's say A matrix and B matrix are given. So A matrix is 2 by 2, B matrix is 2 by 1. Here n is equivalent to 2. Okay. So now we write the S matrix. How do you write S matrix? When n equal to 2, A power 2 minus 1B. Okay. So that is equivalent to what? AB. Okay. So that's why S will be B and AB only up to this term here. So you can find, you can write B. So S equal to, okay. So first you write the B, what is B? 1, 0, then AB. So AB is A multiplied B. So minus 2 multiplied 1 plus 1 multiplied 0. Okay. That will be minus 2. Okay. Then the 0 multiplied 1 minus 1 multiplied 0 is 0. This is my S matrix. Okay. So how do you find the rank of S? Okay. You take the det. Okay. So det here, det of S is nothing but 0. Okay. When det is equivalent to 0, we say that inverse does not exist. So it is called as the singular matrix. Okay. Singular matrix means what? Rank is what? Rank of S is how much? It is not equivalent to 2. Okay. It is, what is the rank here? The rank will be
1.
1, which is not equivalent to 2. Sorry. Okay. So which is not equivalent to 2. Okay. So that is not equivalent to n. Okay. Then you can say that system is uncontrollable. System is uncontrollable. Is this clear? Any doubt?
Sir, if the rank is 2 and the rank which means n is 2, if
Yes.
a determinant of the s is also 2, then it is controllable.
Sorry.
Means you have written rank
Ah,
of s is equals to 1, which is not equal to 2.
yes.
Explain this line, please.
Here, what the uh, debt is equal to 0. Agree?
Yes, sir.
Yeah. So when debt is equal to 0, the rank will not be equal to 2. It's not full rank. Okay. So how do you find the rank? The rank is next level matrix, which is nothing but 1 by 1, which is not equal to 0. Hence rank is 1.
Okay.
Okay.
So,
Mm.
yeah. Okay, got it.
Yeah, hence rank is 1. But here we don't need to check whether the rank is 1 or 0 or something else. Okay. We just need to check whether the rank is equal to n or not. Okay. Here rank is not equal to n. Hence, system is uncontrollable. Okay, now let us go back to the definition. Okay, here uncontrollable means, again, look at this definition. Okay, I said that so system is controllable if there is an input u of t is existed which can take the system from initial state to the final state. Am I correct? Right, that's what I told the controllability definition is. Correct?
Yes,
Right?
sir.
Any, yeah. So now for that example, we got system is uncontrollable. Uncontrollable means there is no input u of t is existed which can take the system from x of t naught to x of tf. That is the meaning uncontrollability means. Okay, you cannot do anything, you cannot control the system. Clear? That is the definition. Okay, when, because this rank condition is not satisfied. Is it clear? That's the definition. Okay, so any doubt here? Okay, so again, so let us say when n equal to 3, okay, if n equal to 3, can you tell me for S matrix? S will be what? B, A, B. Okay, so here you'll get what?
A square B.
A square B. So this will be your matrix. Okay, so for this, again, you have to find. Okay, again, you have to find the det and find the rank, whether it is equal to 3 or not, because n is equal to 3. That is how you will decide whether the system is controllable or not. Okay, now, if the system is controllable only, okay, then we will consider this case, taking u is equal to minus kx and then go up to this point. Okay, otherwise we cannot go. Okay, so that is the basic necessary condition. Okay, so doing the state feedback, system is controllable only, we can do that. Similarly, now we are going to see the observability definition. Okay, again, we will get the similar kind of definition for observability. If system is observable only, we can design this observer. Okay, let's go back and see and come back here. Okay, so for example, so you can also check this. Okay, let us say you have this x dot is equal to ax plus bu. Okay, so you are checking directly physically by using without using this yes. Okay, so let's say you take this transformation, okay, which we call similarity transformation. Okay, here x is the state, so we start with y is equal to px. Okay, then take the derivative y dot p multiplied x dot, then substitute this x dot from this equation. Okay, so then finally you will write y dot is equal to ay y plus by u, where ay is nothing but p inverse, b is nothing but pb. Okay, so we started with this equation. Okay, we have transformed into this similarity transformation equation if p inverse exists. Okay, so now you can see that, let us say if you are taking some matrix P where P inverse exists and do the calculations for the same matrix AB. So this is our A matrix from the previous example. Okay, so this is what we got. Now here you could see here what happened. So you could see first equation. Okay, first equation, what does it indicates? Okay, so in the first equation, y1 dot equal to, what is this equation? Can we write y1 dot equal to what? Minus 2y1 plus u of t. Am I correct? What is y2 dot? Okay, minus y2. That's it. Am I correct? Yes or no?
Yes, sir.
Yes,
Yes,
sir.
sir.
So in this, we can easily see that first term has the input. first equation has the input, second equation there is no input, correct?
Yes, sir.
There is no u. Okay, so that's why it is, this system is controllable. If there is no input, we cannot control this y2 state variable. Okay, the u of t can only affect y1 but not y2, so the system is uncontrollable. This is how you can see physically. Okay, so that's the same thing we are uh, proving here by finding the rank of this. Yes, is it clear?
Yes, sir.
Yeah. So now that is about controllability. Okay. First, whenever we wanted to do the state feedback, so checking this controllability is must. Okay. Next. Okay. Next is observability. Okay. So here observability is, system is completely observable if every state variable of the system affects the sum of the inputs. Okay. Similarly, again, here also we see the general definition. So considering this, particularly the output equation. Okay. So now we can read this definition, this particular definition. Okay. The state x of t naught. Okay. So that is the state at a time t naught. It is observable. Basically, observable means possible to estimate. Okay. So if any given input u of t, okay, there exists finite time tf is greater than or equal to t naught. The knowledge of u of t, okay, knowledge of these matrices a, b, d, e, okay, these system matrices, okay, and the output c of t, they are sufficient to determine x of t naught. Okay, so you can find, if you know, meaning is that if you know all these matrices, okay, all these matrices a, b, d, e, c, output, input, if you have the knowledge of these matrices, you can easily estimate x of t naught. That is what is the meaning of the x of t naught is said to be observable. Okay, similarly, if every state, okay, is observable, okay, then we can say that system is completely observable, or simply we can say observable. Okay, so let me make it simple again. Okay, so the state x of t naught, okay, is observable. Okay, it is possible to estimate x of t naught. That is nothing but the state at initial time. Okay, to observe that, we require only the knowledge of these parameters: input, output, and matrix a, b, d, e matrices. Okay, if all these states are observable, then we can say that system is completely observable or simply observable. Is this definition clear? Okay, to find the initial state of the system at t is equal to t naught, x of t naught, we require the knowledge of this input, output, a, b, d, e matrices. That is the meaning of observing x of t naught. Is this clear?
Yes, sir. And it will be more clear
Yes.
when we will take an
Yes.
example.
Similarly, again, observability also will have this condition. Okay, so this V here is called as the observability matrix. Okay, so V is called observability matrix. Okay, so this matrix is D transpose, A transpose, D transpose, etc. A transpose, N minus 1, D transpose. Okay, so where A is nothing but system matrix, D is nothing but the output matrix, this matrix. Previously, controllability is only in terms of A and B. Okay, observability is in terms of A and D. A and D. Okay, so A and D. Okay, similarly, here also we check the same thing. So you check the rank condition N. Okay, so if that rank is full rank, then we can say that AD is observable. AD is observable. That is the meaning. Okay, so same kind of example you can have. Okay, so let me show you that example. Yeah, just a minute. Yeah, you can see this example. So we have A matrix and we have C matrix. Here C matrix is nothing but D matrix over there. X dot is equal to AX plus BU. So Y is equal to CX plus DU. Okay. Here, so the observability matrix is like this. Okay. So that is like O equal to C transpose. Okay. A transpose, C transpose, etc. Sorry, next term is A transpose square, C transpose. Let me write it again. So same equation. So C is nothing but C transpose, A transpose, C transpose, A transpose square, C transpose, etc. So A transpose N minus 1, C transpose. Same equation. Okay. If you write it in the column matrix. Okay. So now for n equal to 2, okay, you'll have C is equal to C transpose. Okay. You'll get 2 minus 1 is 1. That means A transpose C transpose, which is equivalent to this. This should be O. Okay. So which is equivalent to this. Both are same. Okay. So now, write down C matrix and C transpose, A transpose, C transpose. Okay. So both put together. So this is the O matrix, observability matrix. Okay. So here the rank is 2 because data of O is 1. Okay. Then the system is observable. Again, what is the meaning of observability? Okay. So follow the definition. Okay. So if we have the knowledge of input, output, okay. So from this, if you have the knowledge of the input, okay, the output Y, all these matrices A, B, C, D, okay, then we can find the initial value of X of T naught, okay, state at a time T naught. It means that we can find all the states. That means we can find all the states like X is equal to, so X1 of T naught, X2 of T naught, etc. Xn of T naught. That is the meaning. Okay, we can observe. Okay, or we can estimate all these states. Is this clear? So this is the meaning of the observability. Okay, any queries? The basic meaning. So let me go back to the example again. So the first here. Okay. So first one, what we are trying to do here is, so we are trying to do the state feedback design. Okay. For that, the controllability is must. Okay. Here we are trying to design the observer. Okay. For that, the observability is must. Okay. So first what we do is to find this K. Okay. So our system, the plant must be controllable. Okay. Here from the output, given output Y, okay, to find X cap, to observe X cap, that means that is nothing but the observer design. The observability condition must be met. Okay, these are the two meanings. Is this clear? Any queries? Any queries? Any queries?
No, sir.
Yeah. So now we are going to see the next part. Okay. Next part is how to find this K. Okay. That means that how to do this controller design U is equal to minus KX. Right. That is one topic that we will see today. Then second topic is how to do this observer design. That means given output Y, how can we find this X cap? Okay. So first we are going to see this part today. Okay. The next topic is this one, observer design. Okay. So we call this is as the pole placement technique. Okay. This is called as the observer design. Okay. So once you see these techniques, you'll understand these two images much better. Okay. So let me show you that. Okay, so let us start here. So we know that the location of the poles is very important. Already from the starting weeks, we saw that the location of the poles decides the system stability. Okay, whether the system is stable or unstable, we can simply say by using the location of the poles. If the poles are existing in the LH side of the J omega axis, okay, we can say that system is stable. If any pole existing on the right hand side of the z omega axis, okay, we'll say that system is unstable. That is one concept which you have learned. Okay. Then next in the advanced topics, we also have seen location of poles not only decide the stability, but they also talks about the transient response. Okay, they also impact the settling time, overshoot, and sometimes they also reject these disturbances. Okay, so these are many things connected with the location of the poles. Am I correct?
Yes, sir.
Right,
Yes,
because
sir.
we have seen in some of the examples. Right, now the question uh, is it possible to locate the poles wherever we are interested or to our desired locations? Okay, so that is nothing but the pole placement method. Means placing the poles to our desired locations. Okay, now we are going to see this pole placement method. Okay, so now again you can see we just saw this AB controllability. Simply we check the rank condition for this controllability matrix. Okay, which we also called as the Kalman rank condition. This was derived by this person Kalman. Okay, so we check the rank of this matrix C. Okay, so if the rank is less than n, okay, we check, we'll say that system is uncontrollable. Okay, so then later we also see that we also saw that the it is somehow connected to the pole zero cancellation. Okay, so uh, to first of all, to do this pole placement method, we are trying to placing our poles to the desired locations. Okay. So the basic condition, necessary condition is the system must be controllable. A B controllable. It means that the rank of this C matrix, okay, so must be full rank. Okay. So the question is, how do we change the location of the poles? Okay. So the first assumption is that system is fully state controllable. Okay. Then you can see here now the state variables, they are available for the feedback. Now you can imagine that first image. Okay. So the first image says that we have x dot is equal to ax plus bu. Okay. Here we find x. Okay, so this X is available for the feedback. That is the assumption. Then that feedback we give it here. Okay, then compare with R, you get our output here. Okay, so it means that the state variable X, that must be available for the feedback. That must be available for the feedback. So that is the basic necessity condition for the doing this pole placement controller design. Okay, so in general, what we do, okay, so generally we have this classical approach. Okay, so we have seen already previous examples. If you know your peak overshoot, okay, and settling time. Okay, so if you remember those formulas and if you solve those equations, you can get the values of omega n and zeta. Is that clear? We solve some examples, correct?
Yes, sir.
Okay, so once we have omega n and zeta from the second order system, second order transfer function, we have this characteristic equation. Okay, so these characteristic equation, if we substitute them, okay, we get our roots. These roots we also call them as the dominant poles. Okay, dominant poles. Okay, so generally what we do is, okay, so we place all the rest of the poles. We consider these two poles are the dominant poles. We place all the rest of the poles left side of these two are the dominant poles, let's say. Okay, so the red colors are the dominant poles. Then we place all these poles left side of these dominant poles. That is our classical approach. Okay, but what we do differently here is, okay, we try to force all the poles, including dominant poles, to place at our desired locations. Okay, not just dominant poles, all these poles, all these poles. Okay, so we try to place at the desired poles. Okay, for that, the necessary condition is the system must be state controllable. System must be state controllable. Okay, that is necessary and sufficient condition. Let's see what it is. Okay, so in pole placement design, basically what we do is we know that this is the state equation we have. Okay, now we consider our controller to be like this: u is equal to minus kx. Okay, substitute that into this equation in place of u. You get ax plus b multiplied kx. So we get what? A minus bk. Okay, replace that a minus bk with, let's say, ACL, which is the closed loop A matrix. Okay, this we also called as the state feedback form. Okay, this is your ACL. Okay, now how does this equation looks like? This equation, x dot is equal to ACLX. Am I correct?
Yes, sir.
Yes, yes,
Yes,
right.
sir.
So now, if you find the characteristic equation for this, characteristic equation means for this characteristic equation is Si minus A equal to 0. Okay, for this, the characteristic equation is Si minus ACL, that equal to 0. Okay, so that is nothing but this. Okay, so basically, what is the characteristic equation here says you will get like s power n plus alpha 1, s power n minus 1, etc. plus alpha naught, final equation equal to 0. Okay, so if you put it into roots, you can write it like this. Okay, it means that what you are trying to do, so you are equating your characteristic polynomial with these roots where mu1, mu2, etc., mun are the desired poles where you are interested to place your poles. Is this clear? Then what we do is in the left hand side, okay, we have one polynomial. Right hand side, we have another polynomial. Okay, we compare both. Okay, then we find the coefficients of this K matrix. Okay, that we will see in example. Is this process clear? Okay, let me show you an example. This is what we do. First, we will check the controllability. If controllable only, then we can go to the next step. Otherwise, we'll stop there and say that, okay, system is not controllable. Okay. Then we define this K matrix, K1, K2, K3 depends upon the order. Okay. Then substitute K here in this matrix. Okay. Find this polynomial. Find this polynomial that will be in N. Okay. Then you have your desired poles, mu1, mu2, etc., mu n. Then find this polynomial. Okay. Then compare both these sides, powers, compare powers, and solve for K1, K2, K3. K1, K2, K3. Okay, this we can easily find if the powers are less than or equal to 3. Okay, so let me show you that example. Okay, let's say, so let's say we have this system x dot is equal to ax plus bu. Let's say A matrix is given to you already. Okay. Then you took this Si minus A equal to 0 determinant. Okay. So that gives this characteristic equation s cube plus 6s square plus 11s plus 6 equal to 0. Okay. Now if you find the roots of this, okay, you got s is equal to -1, -2, -3. Where those roots are existed, all those roots are existed on the left hand side. Am I correct? These points.
Yes, sir.
Okay, all those roots are existed on the left hand side of j omega axis. Okay, but okay, you want your desired poles to be like this. Okay, so s is equal to -1, you don't want to disturb. S is equal to -2, you don't want to disturb. -3 pole, you want it to move to -2. Okay, you want it to have 2 poles set to -2. Okay, so due to your requirement. Okay, so the question is how to place the poles to the new locations, desired locations. Okay, for that purpose, what we do is first we start with this u is equal to minus kx, where k is nothing but k1, k2, k3. Okay, k1, k2, k3. Okay, so now we take like this si minus a minus bk. Okay, so given a and b matrices, let's say a and b matrices are given to you, which I have not shown here. Okay, that gives this characteristic polynomial. Okay, now we have these 3 poles, s is equal to -1, -2, -3. Okay, which gives multiplication gives this characteristic polynomial s plus 1, s plus 2, s plus 2. Okay, now we have these 2 polynomials. Okay, you can compare. Okay, so if you compare, what do you get? So 6 plus k1 and 5, 11 plus k2, 8, 6 plus k3, 4. Okay, these 3 equations. Okay, which gives you k1, k2, k3 are -1, -3, -2. Is this clear? Is this clear?
Yes, sir.
Yeah. Once you substitute k is equal to -1, -2, -3, these 3 values. Okay, and so and what you do is x dot is equal to ax plus b minus k x. Okay, and you get what? A minus bk x. This is nothing but ACL. Okay, once you have ACL and find the roots. Okay, can you tell me what are the roots are going to be for the ACL? Can you tell me what are the roots for ACL?
Sir, -1, -3, -2.
-2.
Yeah.
because
And
these are our desired poles.
yes,
We
sir.
found our K matrix. Okay, we found our K matrix to equate it to the desired poles. So this is called as the pole placement technique. Is this clear? This is called as the pole placement technique. Okay, I'll give you 5 minutes time. Okay, yeah. So can you solve this problem as a surprise test? Then we will shift to the next topic. Okay, so take the same example and solve it. Get k is equal to -1, -3, -2. Okay,
Sir,
yeah.
uh, what are you saying?
Same solve
What?
this problem as a surprise test.
Then K equal to?
You should get the same answer. K is equal to -1, -3, -2. Oh, I'm sorry. I'm not given this A and B matrices.
Yes,
Correct?
sir.
Yeah. Just a minute. Okay. Let's go to the next topic. Is this clear? Any doubt? Any doubt here in this method? Any doubt? So this we call it is as a pole placement design method one. Okay. This is easy when your order, when the polynomial is of order less than or equal to 3. Polynomial of order less than or equal to 3. Okay. So then method 2. Suppose if the order is greater than 3, okay, so you can implement this method 2, okay, and you have method 3 also. Okay, let's see this method 2. Okay, so first in the previous class we have seen this controllable canonical form. Okay, so this form, you remember this controllable canonical form, CCF form. Okay, so you have this x dot is equal to ax plus bu. So the controller is minus bk. Okay, where k is equal to, sorry, this is kx. Okay, u is equal to minus kx. K is equal to k1, k2, kn. Okay, so controllable canonical form A matrix and B matrix we can write like this. Okay, given the differential equation, you remember that. So if you have differential equation, okay, so that is like minus, let me write it, a n minus 1 d n minus 1 y by d n minus 1 plus a n minus 2 d n minus 2 y by dt n minus 2, etc. The last term is minus a2 d square y by dt square plus a1 dy by dt plus a naught y. Okay, so same thing, function of u. You remember that previous class we have seen.
Yes, sir.
Yeah. So this we can put it into this CCF form, controllable canonical form. Okay. Now we have this closed loop matrix ACL. Okay. Now what you can do is same process. Okay. So take this ACL matrix. Okay. Then you have this A and B matrix. Okay. So find out is ACL expression in terms of matrix. Okay. This is what is this. Okay. Substituting K along with AB, you get this matrix. Now compare both. Now compare both. So all these the terms are going to be equivalent to this. So whenever you have this, mu1, mu2, mu n are the desired poles. Okay, we will have this polynomial. Okay, once you have this polynomial, you can compare these polynomial coefficients with this. Okay, you can see this. So a naught plus k1 alpha n. So alpha n is nothing but a naught plus kn k1. Alpha 2 is nothing but a1 plus k2. So etc. You can compare every term and get the values of k1, k2, etc. All the other values. Okay. So simply what we are doing is if, okay, if the system is in the CCF form, controllable canonical form, you can directly use this methodology. So that we call it is as a method 2. Okay, and find the K1, K2 expressions. So gain constants. Okay, so example also you can see. So same example. So when A matrix is given, okay, so this is the characteristic equation, Si minus A det equal to 0. Okay, if the given system is in CCF, okay, the differential equation, we have these coefficients from the differential equation. Okay, now if you wanted to place the poles at to -1, -2, -3. Okay, so multiplying each one gives you this differential equation. You have this alpha naught, alpha 1, alpha 2. Okay, so these three values. Okay, now you can compare and find the K1, K2, K3 exactly from the equation. So this is the K 2, 3, 1, which is nothing but U is equal to minus Kx. Okay, which is nothing but minus K1, K2, K3, X1, X2, X3. Okay, which is nothing but minus 2, 3, 1, X1, X2, X3. That is nothing but minus 2x1 minus 3x2 minus x3. That is the expression for u. Okay, that you will substitute in x dot is equal to ax plus bu in place of u. Okay, once you substitute, you will get x dot is equal to aclx. Okay, this acl, okay, will have eigenvalues. Okay, if you calculate it, you have eigenvalues of -1, -2, -3. Is this clear? That is how it looks like, the pole placement technique. Clear?
Yes, sir.
Any query here in this? Okay, please check once. Just give me 2 minutes time. I'll be back. hear me? Yeah. Thank you for waiting. Yeah. Is there any query in this? So can you hear me?
Yes, sir.
Yeah. Is there any query? This is the method two. If the system is in controllable canonical form, okay, you can find the K vector in this way. That is part of the pole placement technique. Okay. So method three. Okay, suppose if in case if that given in the method 2 itself, if x dot is equal to ax plus bu, if it is not in the canonical form, okay, what you can do is you can uh, convert that into canonical form by doing this similarity transformation. Okay, so this transformation, and you can convert that into canonical form and follow the same procedure, and easily you can find the K matrix. Okay, that you can understand it easily. So then method three also called as the Ackermann formula. Okay, in the Ackermann formula, basically what we do is we use something called as uh, Cayley-Hamilton theorem. Okay, Cayley-Hamilton theorem for a matrix, what it says is, okay, given matrix, okay, so the characteristic polynomial is det of lambda I minus a equal to 0. Okay, so if we expand it, if you find the det, okay, so you will have this equation. You'll have this equation, which we call it is as the pi of lambda. Okay, the polynomial. Okay, Cayley-Hamiltonian theorem says that every matrix A satisfies its own characteristic equation. Satisfies its own characteristic equation. It means that if this is the characteristic equation, okay, okay. So according to Cayley-Hamiltonian theorem, simply you can replace lambda with matrix A. Same equation. So that is the meaning of every matrix satisfies its own characteristic equation. Okay. So this method uses this Cayley-Hamiltonian theorem. Okay, method uses this Cayley-Hamiltonian theorem. So basically here what we do is, so uh, we know this form where x dot is equal to ax plus bu. If you substitute u is equal to minus kx, okay, you get this matrix a minus bk. That means this matrix is converted to a minus bk multiplied x. Okay, that a minus bk we define like a tilde. Okay, so then we define characteristic polynomial, okay, with substituting a tilde, and mu1, mu2, mu n are the desired poles location. Okay, so you can write this part as si minus a tilde, and this side you can write as polynomial. Okay, is this clear? Any doubt in this?
No, sir.
Yeah. So now we are going to use this Cayley-Hamiltonian theorem. Okay. So to find this K matrix. Okay. So for example, if you consider n is equal to 3 as an example. Okay. So a tilde square, a tilde cube. Okay. These are the three expressions. Okay. Substitute them into this equation. Okay. So then you'll have the characteristic polynomial as pi of a tilde. Okay, substituting these three expressions for n is equal to 3. Okay, you can understand these expressions. Then compare with the using the Cayley-Hamiltonian theorem. Okay, so pi of a tilde expression is this. Then you can write pi of a. Okay, comparing both, pi of a is this matrix, which is nothing but the controllability matrix. Okay. So if this controllability matrix is singular matrix, non-singular matrix, that means inverse exists, you can bring on to this side. Okay. Then multiplying both sides 0, 0, 1, which makes these two terms goes to 0, only k would be left. Then finally we can write k as 0, 0, 1, the controllability matrix, and pi of a, which is the characteristic polynomial of a matrix. Finally, the k matrix. Okay, so 0, 0, 1, C matrix, controllability matrix, and characteristic polynomial. That is direct equation. This we call it as a Ackermann formula. Okay, so only thing is that you need to find this one. Pi of a is characteristic polynomial. Okay, first what we do, so you find given A matrix, okay, find its characteristic polynomial, that is nothing but pi of lambda, which is nothing but Si minus A determinant. Okay, which you will get lambda power n alpha 1, lambda power n minus 1, etc., alpha 2, lambda n minus 2, etc., alpha n I. Okay, in this, wherever there is a lambda, substitute A. Okay, which you will get this equation. Once you have this pi of A, okay, so given A and B matrices, you can calculate this controllability matrix. Then multiplying all put together will give you K matrix. Okay, which is nothing but the Ackermann formula to find the K. Is this clear? This step? This step clear? Any doubt?
No, sir.
No, sir.
Yeah. You can see this example also. Okay, so for 3 by 3 matrix, okay, A and B matrices are given. Okay, so we are using the state feedback. U is equal to minus kx. Okay, the desired poles you wanted to place 3 poles at minus 2 plus J4, minus 2 minus J4 minus 10. Okay, these are the 3 locations, mu1, mu2, mu3. Okay, so now directly finding the first C matrix, because it is the 3 by 3. Okay, so A power 3 minus 1 B, which is nothing but A square B. That's why we have highest till A square B. So once you have C matrix, okay, so the rank is C because the data of C is not equal to 0 and system is controllable. That is our first step. The first step 1 is to check the controllability. Okay, next method 1, what we do, so since we have A matrix, okay, so take Si minus A equal to 0, which will give you this equation. Okay, which will give you this equation. Okay, so the coefficients are these: A11, A01, A15, A2, 6. Okay, then characteristic equation for the desired poles location. These are our desired. Okay, so then this is the polynomial. Okay, then you have your coefficients are alpha 1, alpha 2, alpha 3. Okay, by comparing the coefficients, you will get K is equal to 199, 55, 8. It means that this is the desired polynomial that you can equate it to Si A minus Bk. Yep, this polynomial you will get it in S cube. This polynomial. Okay, so you will compare this coefficients, this polynomial coefficients, you'll get this K matrix. That is using method 1, direct. Okay, this is method 1. In method 2, what we do? Okay, method 2 you try to put the equation in the assuming that given CCF form is possible, controllable canonical form. Okay, you'll find this. Okay, then this is the desired. You compare both. You compare all the coefficients. You'll get the same K matrix. Okay. In method 3, Ackermann formula, this equation we know already. Okay. So 0, 0, 1, C matrix. Okay. Then characteristic polynomial of A according to the Cayley-Hamiltonian theorem. Okay. So this you will get as pi of lambda. Okay. In this, replace the lambda with A matrix. Then you have this equation. Okay. So this is the pi of lambda. That is lambda cube plus 14 lambda square plus 60 lambda plus 200i. Replace lambda with A, that becomes pi of A, this matrix. Then you have controllability matrix. Okay. Substitute everything into this equation, which will give you the K. So same as that of the previous two methods, 199, 55, 8. Okay. So this method is called as the pole placement technique. Basically what we are doing, so first step is you need to check the controllability. Okay, controllability means write down the controllability matrix, check its rank condition. Okay, so rank of C, if it is equal to N, then only you can go for the pole placement technique. Okay, basically pole placement technique, what it says, you wanted to place the poles to these desired locations. Correct? To these desired locations, you have three methods. In first method, direct method, okay, where you compare this polynomial with this. Second method, if the system is in the CCF form, you can find the K. Third method, using the Ackermann formula, you can find the K matrix. Is this clear? Any did you get the idea?
Yes, I got the idea.
Yes, sir.
Yeah. So this directly again you can see this picture. Okay. So the pole placement technique related to the first one. Okay, where X is available to you all the time, then you take U is equal to minus KX. Okay, and then write down this equation. Okay, compare the both the polynomials and get the K matrix. Okay, this is the pole placement technique. Wherever by using this technique, we can find the K in such a way that we can place the desired poles wherever we are interested in. Okay, this is called as the pole placement technique. So the first condition is we must check the controllability. Okay, if it is controllable only, then we can follow the rest of the method. Okay, then now to give the idea for the second one. Okay, so we are saying that all the time the X is available for the feedback. X must be available for the feedback. What if Fx is not available? Only Y is available. Okay, to apply the pole placement, what do you need? You need X, correct? You need X, right? To find X, what we do? We design something called as the observer. Where what this observer will do? Observer takes the output Y. Using that output, it estimate the X cap. It estimate the X cap. Then you can directly follow the next pole placement method. Is this clear idea?
Yes, sir.
Yeah. So that is called as the observer design, which is also called as the output feedback and observer. Based on output feedback, we design the observer. Okay, that we will see in the next live. Okay, this is the overall concept. Controllability related to the pole placement technique to place our poles in the desired location. Okay, so for that, the basic assumption is always the X is available. Okay, whereas if X is not available, only output is available. Okay, something like you can see here. If output is like this, what does it mean? Y here is equal to only X1. Okay, output is available directly. We can say that X1 is available. We don't know anything about X2. So in that case, we need to estimate or we need to observe X2 also. Okay, for that we develop this. We check the observability. Then if it is observable, then we design this observer design based upon the output feedback. Okay. I'll share this both the notes. Okay, you can go through that all the three methods of pole placement and the logic behind this observer and the pole placement technique. Then you can ask me any doubts in the next live.
Sir,
Okay. Yeah.
in exam we
Yes.
can do any one method, no? Or it is specified to do that?
Oh, pole placement technique.
Yeah, yeah.
Yeah. Generally, you can do any method. I think we don't specifically ask because this is the ending module. Okay, we don't specifically ask. You can do any of the three methods. Okay.
Okay, sir.
Yeah,
And
yeah.
in same
Hmm.
there is pen paper or
Sorry, Ensign.
pen paper or computer based CBT.
Uh, I think we'll give some instructions. I mean, I'm not sure yet at this moment, but I'll answer this in the discourse.
Okay.
Okay.
And sir, there is
Yeah.
another question for that is week 10, question number 5. I have
Yeah,
told you.
yeah. We already sent the email to the moderators. They will update that. Not an issue.
Till now it is not corrected.
It's
Yeah.
not corrected.
No, no,
Okay.
no, sir.
Okay. Okay. I'll note it down and inform them again.
Okay,
We'll
sir.
make sure that it will be updated soon.
Okay, okay. Okay, sir.
Yeah. Okay. We'll stop here and continue in the next slide. Thank you.
Thank you, sir.